So here we go. All right. So we're actually going to be finishing up our notes packet today. We're going to get through the rest of it. We have quite a bit to get through. So I don't want to dilly-dally too much here. All right, so if you would open up there to section 5.3 on your notes, okay, the definite integrals. We'll get into things. Okay, hope you all had a restful break. You're counting how many more days till Christmas break? Winter break, I mean. Yeah. All right, so let's review, since we've had a lot of days off and lots of food since then and sleep as well, so maybe we've lost ourselves just a little bit here. So remember, we're talking about integration, all right, antiderivatives, and basically kind of like going backwards from differentiation, right? Kind of like inverse of differentiation, right? We learned all of these different rules, okay, all these different new integration formulas that are essentially derived from, derived from our derivative rules, right? They just go backwards, right? Where we took the derivative of tangent of x, for example, and that was secant squared, we also know now that if we integrate secant squared, we end up with tangent of x plus c, right? Plus c, that constant of integration there. Okay, we learned to be very careful here where we saw something like the integral of 1 over x. Okay, we might be tempted to rewrite that as x to the negative 1 and then integrate that using the power rule, right, by adding 1 to our exponent there, and we get x to the 0 and then divide by our new exponent 0. Remember, that's not a power rule, right? 1 over x or x to the negative 1, that's the same thing as, well, when you integrate it, it's the natural log of the absolute value of x. Again, plus c. So don't forget those integration rules. Right? We learned about how we had to like rewrite things sometimes, right? Sometimes you have to distribute. Sometimes we had to square things out, right? Sometimes we had to rewrite a fraction, right, as x to the negative 1/2. Okay, that's helpful. You know, some of these, the trig stuff, well, I guess we didn't have to rewrite the trig stuff there. But anyway, you get the idea, okay? Sometimes you have to rewrite things before you can integrate them to match our rules. Then we found particular solutions, right? We integrate our function here and get something with a c in it, and we use the piece of information. We know that, for example, in this case, we have our solution has only one curve that passes through the point 2, 4. So we use that point 2, 4, plug it into our solution there, right? 4 in for the y, 2 in for the x's, and solve for our c value and get our particular solution for this particular piece of information. All right. We talked about position, velocity, and acceleration stuff, right? Where when we took position and went to velocity, went to acceleration, we differentiated, right? You take the derivative to go from position to velocity to acceleration. To go from acceleration to velocity to position, you go backwards, you integrate, okay? And of course, every time you integrate, you have a new constant integration. Okay, so sometimes you have to use, a piece of information here to get those missing c values and stuff, right? Okay. Still want to be able to answer questions about speed. Still want to be able to answer questions about, after how many seconds after launch the ball is back at its initial height. Those kind of questions, right? Still want to be able to find changing in direction and all that stuff. Okay. Then we kind of changed gears a little bit. Talked about this concept of area under the curve. All right, using like geometric formulas to help us find area under a curve. All right, and then we talked about approximating area under a curve, where a geometric formula wouldn't necessarily help us out. All right, actually, where a geometric formula wouldn't necessarily help us out here. So we have the right endpoint approximation, okay? We have our left endpoint approximation there, example, and then we have our midpoint approximation, okay? Please be aware, right, of the different kinds of behaviors that we have. Thank you. So let's see here. Again, keeping in mind when we have over approximations or under approximations, right? I think it's pretty clear to be able to determine. Again, draw a picture if you need to for the left endpoint, right endpoint. It's pretty clear here, right? Okay, a right endpoint for the decreasing function. Okay, right endpoint approximation for a decreasing function is an under approximation, whereas the left endpoint for a decreasing function is an over approximation. And then those behaviors flip-flop when you have an increasing function, right? Midpoint is a little bit trickier. Midpoint is an over for concave down and an under for concave up. Okay, so concave down over for midpoint and concave up under approximation. And then for the trapezoidal rule, that flip-flops, okay? So keep that in mind too. Again, we did some more practice of that, more practice there. And you guys had the homework there. Okay. Then we talked about the trapezoidal rule. Okay. So again, trapezoidal rule: overestimate for concave up, underestimate for concave down. Okay, that is reverse from the midpoint. Midpoint is overestimate for concave down, underestimate for concave up. So it's reverse of the midpoint. So keep that in mind for the trapezoidal rule. Okay. Approximation, We went through like using a table and stuff like that, and the meaning of it. Uneven interval widths, don't be thrown off by that, right? Just be careful if your table, for example, is not going up by the same increment each time. Just understand that, right? The width changes. Here we go from 0 to 3, so the height of our trapezoid is 3. Here it goes from 3 to 4, height is 1. Here it goes from 4 to 8, height is 4, 2, so on and so forth. So those widths, okay, or the widths of our rectangles, I guess, change in those cases. So just be aware of that. All right, and that brings us up to here, where we are now. So in the previous section, we estimated the area under a curve using a finite number of rectangles. Using the sum of those gave us an estimate for the area. Let's see if there is a way to find the exact area under a curve. Okay, so we're going to start off with let f be defined on the closed interval from a to b. Okay, because again, we need a closed interval. If we just kind of find the area under a curve, it might be infinite, right, potentially here, so we want to kind of limit ourselves. And let delta x sub k be the width of the kth subinterval of that interval AB. Okay? And we're going to have, in this case, so we're going to have equal widths for each subinterval. We're not going to worry about, different widths for the subintervals and stuff like that. So, meaning that each subinterval has a width represented by, well, how do we find the width of a subinterval normally? If we go from, let's say, here's going to be A, to, let's say, here will be, actually, I got to maybe go to here. Here is B, okay? And we want to divide that up into n subintervals here. Well, we take the endpoints, B minus A, right, and divide that by n, the number of subintervals that we want. Okay, so B minus A divided by n, that will be our, our subinterval width, and we'll call that just some tiny change in x. Okay, because again, we want that width to be very small. If we're talking about, well, having a lot of rectangles here, that interval is going to be really small because we're going to take our b minus a and divide it by a very large number since we want a lot of rectangles. Okay. So then, if that is our subinterval width right here, delta x, then a to, let's just say this is our first subinterval here, what will this be? If we start with a and we want this width to be a width of delta x, how can we represent this next endpoint right here of our first subinterval? It would be a plus delta x. Exactly right. Okay. All right. So there's going to be like our first, kind of interval right there. A, starting at a, and they're going to add a delta x to it to get a plus delta x. Since the method of finding the exact area is similar, regardless of if we use left endpoint approximation, right endpoint approximation, or midpoint approximation, we will use just a right endpoint Riemann sum here. Okay, so really the method's similar whether we use left endpoint, right endpoint, or midpoint approximation. We're just going to use right endpoint. Okay. As a reminder, right, a right endpoint approximation is the sum of the area of n rectangles, where the area of each rectangle is found by, so in our cases, right, the width of each of these rectangles is going to be what? Delta x times, and then what determines the height of these rectangles? The y values, or the function values. So we'll do f of, and then we'll just say times our function there, depending on the x value there. Sean, did you have a question, or are you just going to answer?
I was going to ask a question.
Okay, did you still have a question?
Yeah.
Okay, what's your question then?
So on the graph, what would be n? Like, where would n be shown?
So n is like the number of rectangles here. So while if you look here, right, you can count up. There's a finite number of subintervals. I mean, it's kind of hard to represent an infinite number of subintervals there, but imagine there's just an infinite number of like little tick marks here, I guess, kind of thing. So we're showing a finite number, but it really should be like n is going to be like a very large number kind of thing. Okay, so it's kind of hard to represent an infinite number of little intervals though, because well, they're going to be so tiny and it will be hard to draw all that. So we're just going to kind of do this. Okay? So, as you add up each of the areas of the n rectangles, the width remains the same, okay? But the heights change as the function changes, right? Because we're using the same subinterval, so the widths will stay the same, but the height will change because the function is potentially changing there. So we must develop a way to express the changing heights. Since we're using a right endpoint approximation from A to B with n rectangles, the area equals height times widths r. So for this first rectangle here, okay, so we'll say for rectangle 1, which is this guy right here, and we're going to use the right endpoint here to kind of determine that height. Okay, there's rectangle 1. Okay. If we're using the right endpoint approximation here, that means we want to evaluate f at what value here? If we're trying to use the right endpoint approximation to get this area, which endpoint do we want to use to approximate? A plus delta x. So we're going to do f of a plus delta x times, so that's the height of the rectangle, times its width. And what is this width of this subinterval here? Or what represents the width? Yeah, delta x, right? It's the width delta x there. Okay. So if this is represented by a plus delta x, right? We start with a, we went out a delta x to get to a plus delta x. What will this next, how can we represent this next interval right here? What will this next endpoint be? A plus, good, 2 delta x, because we're going out another delta x from the a plus delta x. We add a delta x to this, we end up with a plus 2 delta x, which will then yield another rectangle here. And this will be rectangle 2. Okay, for our second subinterval then, rectangle 2 is equal to f of, what's our right endpoint for this second interval? What's our right endpoint here? A plus 2 delta x, so f of a plus 2 delta x, okay, times delta x. Okay. Let's go ahead and do 2 more here. We'll do the third subinterval and we'll just do like the kth one, you know. So again, the next point here, this will be a plus 3 delta x. Okay, again, we're using the right endpoint here, so we'll just draw the rectangle so that the right endpoint makes our height. And again, the width is delta x, so this should be, rectangle 3 is f of a plus 3 delta x times the width delta x. So you see, as we add up these rectangles, the only thing that's really changing here, the only thing that's really changing with the way we're writing this is the number in front of the delta x there, right? We're just, you know, because it's the right endpoint that's changing. And so then for the kth subinterval, so r sub k, we'll say that's going to be equal to f of a plus, well, if r sub 1 was equal to f of a plus delta x times delta x, r sub 2 was f of a plus 2 delta x times delta x, r sub 3 was f of a plus 3 delta x times delta x, so r sub k should be equal to f of a plus what? K, yeah, delta x. Okay, the number of the rectangle is what you're going to multiply by that delta x. And then times, of course, delta x there. Okay. So again, you clearly can see here there's a finite number of rectangles here, but we're trying to make it so we can then get we're trying to make it so we can have an infinite number of rectangles potentially here. Okay. So the area, okay, because it's now, if we add these up, it'll be a Riemann sum. So the area, which is going to be a right endpoint approximation here, is approximately, right, r sub 1 plus r sub 2 plus dot dot dot. I guess I should do the r sub 3 since we already wrote that one. Plus dot 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 up to r sub k. Okay. All the way on up there. Which, according to the way that we wrote things here, right, so r sub 1 again was the f of a plus delta x times delta x plus f of a plus 2 delta x times delta x plus f of a plus 3 delta x times delta x plus f of a plus k delta x times delta x. Okay, so again, if we want to find then the area of this whole region, we would add up these rectangles. Okay. But of course, when we add up an infinite number of things, when we add up things, right, we have a notation for that, and it's a summation notation. And so we can say that this is the same thing as saying the sum, remember the sigma symbol there? Sum from k equals 1 to n, okay, because we're counting from k equals 1, there's the, 1, 2, 3, and then it'll go up all the way up to k, or n, I guess in this case, for the number of subintervals we have, of f of a plus k delta x times delta x. Okay, so this summation, represents the area under f of x with n rectangles from A to B with the width of delta x. Okay. So we've kind of like created, I guess, a formula, right, or another way to represent these rectangles, right? But now we can do it for any number of rectangles that we want, right? It's just n. If you want 10 rectangles, you can sum from 1 to 10. If you want 100 rectangles, you can sum from 1 to 100 in this formula. Okay? And that's how many rectangles you can get using that formula. Okay. So, questions on any of that so far? Okay, it's a little bit funky here, but we're getting somewhere with this. All right. So turn the page here. Now, this summation, okay, is of a finite number of rectangles, but we want it to become closer and closer to the actual area of the curve, right? Even with a finite number of rectangles here, we're still going to have, some over approximations in some cases, under approximations in other cases, right? It's not going to be perfect, but we want to try and get the exact area. Okay, whoops. So, wrong page there. So if we want it to become closer and closer to the actual area of the curve, we should allow two related things to happen. Okay? The first thing we should do is allow n to go to infinity, which is just the number of rectangles. So we want the number of rectangles to go towards infinity. We want to go to like an infinite number of rectangles. The more rectangles, the more accurate it will be. Simultaneously to that, as n approaches infinity, right? As n approaches infinity, right? So here's like n. What's going to happen to the width of our subinterval as n goes to infinity? It's going to go towards what number? 0. Exactly right. And so simultaneously to that, if n is going to approach infinity, if we're going to have an infinite number of rectangles, our subintervals have to go closer and closer to 0. Okay? So that is the width of the subinterval. Okay, to 0. So those two things are going to happen here. All right. And so if we want n to approach infinity here, okay, we can get the exact area formally by stating it this way. The area underneath a curve is going to be simply the limit as n approaches infinity of the sum k equals 1 to n. I know, it's like we're putting summation and limits together. It's like peanut butter and jelly, right? How can we get any better? Or chocolate and peanut butter, it's just delicious. Some of them I really like peanut butter, I guess. I just put it with everything, so. Okay, times delta x. It's like limits are hard enough on their own. Sums are hard enough on their own. Let's put them together. There it is. Okay, this allows us to find the exact area under a curve, okay, and an interval. But, of course, that's kind of a handful. So we can also change the notation, okay, from the Greek stuff here that you see to a more common Roman, I guess. Apparently this is the there it is, okay? This is it. Okay? So Mathemagic, voila, poof. Okay? So, presto changeo, we're going from this to this, okay? And unlike when we learned derivatives, where we had you guys, remember when we first learned about how we found derivatives, we had you actually do that limit definition of the derivative to some functions to really impress upon you, what was going on behind it. We're not going to do the same thing here. All right, so there will be no problems where I give you something like this and say evaluate it. What I will expect you to do is to be able to, what the expectation is to be able to take this, right, and reinterpret it into this. Okay? Or in some situations, take this and reinterpret it back into this. Okay? So that's the gist of it. And then we'll show you later how to evaluate something like this, where we integrate something from A to B. Okay? But for right now, we're not going to show you how to integrate, how to do this one just yet. Okay? We're just going to say that these two things are the same. Okay? So, this is known as a definite integral. If f is defined on the closed interval ab, and the limit exists, then f is integrable, that means able to be integrated, on the interval ab, and the limit is denoted by this, right? Which is the same thing as saying the integral from a to b of f of x dx. The limit is called the definite integral of f from x equals a to x equals b. The number x equals a is the lower limit of integration, and the number x equals b is the upper limit of integration. Okay? Understand this kind of big idea here, okay? A definite integral is a number. Like this will equal a value, a number, okay? So you can think of it as a number or a value or a quantity. Okay? A definite integral results in a number or a value or a quantity, okay? It gives you a number solution. It is equal to a value. Whereas an indefinite integral, right, when we have no limits of integration, when it's just like the integral symbol, okay, no limits of integration there, that is a family of functions, right? That means, that gives you like the capital F of x plus c, that kind of stuff that we did before, okay? So we're doing a similar kind of process, but the results are different. For a definite integral, when you have limits of integration, you get a value, a quantity, or a number for your answer. When you integrate a function with no limits, you get a family of functions. That plus c, right? It's a family. It creates a family of functions. Okay, for your answer there. So the answer for this, function. The answer for something like this, a number, a value, or a quantity. All right? So, the definite integral of an area as the area of a region. Okay, and that's what we're trying to kind of bring everything together here now. Okay, if f is continuous and non-negative on the closed interval ab, then the area of the region bounded by the graph of f, the x-axis, and the vertical lines x equals a and x equals b is given by this. Okay, so in other words, right, if I draw a function here, call it f of x. Okay, so something like this. I'm not going to be very creative there. There's f of x. Let's just say I've got a here and b here. Okay, this integral, right, is finding the area of the region bounded by the graph of f. So here's one of its boundaries. So this region that's bounded by this part right here. The x-axis, so this is also a boundary right here. Right? And then the vertical lines x equals a, there's a boundary, and x equals b, there's a boundary. And so what region is enclosed by that? It's this region right here. Okay? That region is bounded by all four of those things. And so this equals this area, this quantity. Okay, what that value is. All right? Okay, so let's see how we're going to actually use this. Let's do some stuff. All right. So why don't you guys go ahead, example 1a, you do this one, right? Give an approximation of the area of this curve from 2 to 5 within 4 equal subintervals. All right, maybe I'll help you get started here because those subintervals are a little bit funky. Okay. So how do we find the width of a subinterval here? Well, what's the total distance that we have to go? From what to what? 2 to 5, which is a length of what? 3 from 2 to 5. Okay, and then we're going to divide that total amount there into how many equal subintervals? 4, so we're going to divide it by 4. Okay, so let's see here. Do I have that? Yeah. So like your delta x there is equal to that. So 5 minus 2 is 3, so it's 3/4, or you could say 0.75. Okay. So that means we're going to start at 2. Close, so close. We start at 2, and then what's our next endpoint going to be for our first subinterval? 2.75, or 2 3/4, okay, 2.75. And the next one will be 3.5, and then 4.25, and then 5. And we got our 1, 2, 3, 4 subintervals there, right? You can see them. Okay. So, actually, I said I was going to have you guys do it, and now I'm just going to run through it anyway. So, oh well. All right. So the area for that first rectangle, well, it's going to be the subinterval, right? The width of the subinterval, though, so it'll be 0.75 times f, and we're going to use a right endpoint here, so we're going to do f of which endpoint here? 2.75. And then plus 0.75 times f of 3.5, the next right endpoint. And then 0.75 times f of 4.25, the next right endpoint. And then 0.75 times f of 5, the next right endpoint there. Okay, tomorrow's quiz will be calculator active, right? You'll be able to use your calculator if you want to. But of course, we don't really need to use our calculators for a problem like this, because all we really need to do, we're not quite done yet, we should probably rewrite this. So instead of f of 2.75, since my function is x squared, I can just write 2.75 squared. And then 0.75 times 3.5 squared. 0.75 times 4.25 squared. And then 0.75 times 5 squared. And then you can circle your answer. Okay? So while you can use your calculator to get the final answer there if you really want to, it's not necessary because you don't have to simplify arithmetic. So you can stop right there if you want to. Okay? In fact, I might encourage you to do that just because it saves time. Yeah.
So are we able to just do 0.75 and then all
Prime-
the other values in parentheses?
Absolutely. So alternatively, yeah, you could do 0.75 times and then 2.75 squared plus 3.5 squared plus, and then up to, the 5 squared. Of course, don't do the dot, dot, dots. Actually write that out for me, on the quiz or test. But yes, you absolutely can, just factor up 0.75 there if you want to save yourself all those 0.75s that you're writing. Absolutely. Okay? So this answer, by the way, will be a what? Overestimate or underestimate? I didn't ask the question there, but what do we expect here? Will this be an overestimate or an underestimate? Well, let's take a look here, right? Okay, the graph is x squared. So it's going to look something like that. So, there's, 2, 3, 4, 5, whatever. There's your intervals here. If we're using the right endpoint, so let's say for that first subinterval, right endpoint, it's going to be a what? Overestimate. Okay? And please feel free to draw yourself a little picture if you need to determine whether it's going to be an overestimate or an underestimate, right? Convince yourself whether it's going to be overestimate or underestimate. You don't necessarily have to memorize it. It's helpful. Okay. Of course, this is all, since it's increasing, this will be an overestimate for the whole increasing interval. Decreasing, right, a right endpoint is an underestimate. So it does change depending on the behavior, but it is an overestimate. Okay. So now let's talk about doing the limit definition of it then. Okay. So the limit definition of, and the definite integral representing the exact area. So we're going to do the limit definition first, then we'll show the definite integral representing the exact area. Okay, so we'll go back to our little setup that we kind of, came up with, right? The area for the limit definition is the limit as n approaches infinity of the sum, k equals 1 to n, okay, of f of a plus k times delta x times delta x. Okay, and we just want to fill in some of these values here for this specific situation, for this specific scenario, right? So for example, let me ask you an easy question. What is f in this scenario? It's x squared, yes. We can just say, okay, f of x is x squared. Okay, what is our a in this scenario? 2, right? It's the left endpoint. That's our a, that's our b. So yeah, a is 2, so 2 is going to go in there for a. The delta x, that is the width of our subinterval here. Well, what did we say the width of the subinterval was? 0.75, right? 0.75. But that is if we were dividing into 4 equal subintervals. For this scenario, we're going to be dividing into not 4 subintervals, but how many? An infinite, so let's just put an n in there, okay? So the delta x will be b minus a over n, right? Which is the same formula we always use, but it's the b, 5, minus a of 2, divided by n. We don't know the number of subintervals, so we'll just leave it as n, right? It's going to be an infinite, so that's why n is approaching infinity. So it'll be 3 over n is the delta x. Okay, so let's just substitute this stuff in. I'll hold off on f first. I'll just plug in like the actual values here. So this is going to equal the limit as n approaches infinity of the sum of k equals 1 to n of f of, okay, so a is 2. K, okay, is going to stay k. It's going to stay k. It's kind of like our function, our variable here, because that's where we're counting from 1 to up to n there. Times delta x, which is 3 over n. Times, and then delta x, which is again 3 over n. I did. I'm going to do that next step. I didn't want to do it all at once. I wanted to kind of just get some of the numbers in first, and then. But you're right. You're right, Amanda. We can do it all at once if we want to. Okay. So, the final step, right, is to plug this whole thing into our function, or what's inside the parentheses here, right? So the 2 plus k times 3 to the n, 3 over n, that's going to go into x squared. So this f, it's f of this quantity, so it's going to be still the sum there. Whoops. So the quantity 2 plus, I'm going to make that 3k over n squared times 3 over n. Okay, so there is the limit definition of that exact area. Okay, there's the limit definition of it. Okay, again, we change the f of to be the something squared. F of that something to be that something squared, because that's what the function is there. It's squared. Okay, x squared. So there's limit definition. All right. And then the integral, the definite integral. Well, what's our left endpoint? What's our right endpoint? 2 and 5. So the lower limit of integration, 2. Upper limit of integration, 5. And what's our function? X squared dx. So there's the alternative way to write that in the definite integral representation. That's it. Yeah, right? But again, think about this. This is very similar to what we talked about when we learned about derivatives, right? When we did the derivative, we learned the limit definition first, and then we kind of used that to then, kind of springboard into, the way we're going to do the derivative with the shortcuts and things like that. Okay, different representations. Same idea here, right? We want to be familiar with this representation, but this will be our bread and butter. This is going to be our primary way to do it. We should be able to take this, though, and read what this is going to be. Okay, or actually, I think we should be able to go from here to here. Okay, potentially from here to here, too. Okay, so let's try another one here. So here we're given a definite integral, and we want to write the limit definition of the Riemann sum that is equivalent to the following definite integral. So we've got this, we want to come up with this. Okay, so again, we'll write down here, area equals the limit as n approach. We'll write down the generic kind of formula for it here. K equals 1 to n of f of a plus k delta x times delta x. Remember, this is not on tomorrow's quiz. This is not on tomorrow's quiz. Okay? Not on tomorrow's quiz. So don't fret too much if it's like really weird. Okay, so same kind of questions I asked before. All right, what is our function here? What is f of x in this scenario? 3 natural log of x. Okay, 3 natural log of x. What is a in this scenario? 2, our lower limit of integration. Okay, so a is 2. Okay, what is our delta x? What is our interval subwidth? Yeah, it's going to be 4 over n. 6 minus 2 divided by n subintervals, right? So it's going to be 4 over n. Okay. So again, I'll do the same kind of two-step substitution I did last time. If you guys feel comfortable, you can substitute the whole thing at once. All right. So just take it step by step. I'll leave f there for now. We'll plug in 2 for a. K is going to be k. Delta x is 4 over n times 4 over n on the outside there. Okay, and now we'll substitute this quantity here that's in the parentheses, we'll substitute into our function. And so our final answer, 3 natural log of 2 plus, I'm going to again multiply it to be 4k over n times the 4 over n. Okay, and so there is our limit definition of Riemann sum. So there's the setup. Right. By the way, can we integrate the natural log of x? Do we know what the integral of the natural log of x is? We do not know the integral of the natural log of x. Okay, and in fact, there is no nice rule for the integral of the natural log of x. So we can't do this by hand. We can use our calculators to get it, right? Because our calculators can do this kind of stuff. But we can't by hand. So kind of impossible with what we know. All right, go ahead, try letter B. So you guys go ahead now. Try letter B on your own. All right, this one for real, for real. I'm going to let you do on your own. I got some nice tissues now, yeah. They have lotion on them. They're given to us by SGA, so you can thank SGA for that. They come with germs already too, yeah. Mm-hmm. Pre-germed. Pre-germed.
Wow.
Yes.
Build up some antibodies.
Yeah. Mm-hmm. Think about it. That's what the Kleenex company wants you to do. They want you to get sick, so that way you can buy more tissues.
There you go.
It's their, it behooves them to make you more sick. They don't want you to get better. Is anyone here in Conspiracy Club? There's your next conspiracy. There it is. All right, I just came up with that. I mean, sorry, I read about it on the internet, so it must be true. With 120 people, I imagine it's pretty crazy to try and have a conspiracy discussion anyways.
Because I'm hungry. There's a difference between food tasting good and you just being hungry.
No, but that's an actual thing. They put slight addicting products in order to get people to come back.
No, you're hungry because you don't eat. You starve yourself. You're hungry.
Okay.
Sounds really good right now, though. Some Chipotle.
What's that? We don't touch the function is signed, so it stays signed. We're not integrating it. We're just keeping the same function. Okay, so there's your setup. I guess if you want to, you can make that 15k over n.
Starve myself over. I said I starved myself over turkey break.
Okay, so sign a 15k over n if you wanted to there for one more of a little simplification. Okay, because the 5 times 3, 15k over n. Times the 3 over n.
Yeah, Mr. Whitmire?
I was trying to save on writing, but.
I don't know.
Okay? Yes? So, go ahead then and answer example 3, okay? So, the example 3 here, it's multiple choice. A, B, C, D, okay? And this is the kind of thing that we should be prepared for on the AP test and stuff. This is the kind of question you can expect to see, okay? The kind or style of question you can expect to see. Yes?
Would it be wrong for
P, the one that you just went over, where you just left it sign file, parentheses 3K of rest.
No.
Okay, because it's arithmetic. And
Correct. Correct.
I get how
But just understand that you can multiply together. Okay, so again, try example 3. Take like 30 seconds here.
Happy. Nothing's that bright and colorful at this point. Yeah. I don't know. Bright colors is cold and not bright at this moment.
It's not even cold in here.
It's not even outside.
cold. You won't be outside for like
Oh, let me be happy by shoes.
Okay, so
We're trapped inside.
in this scenario,
The bright colors
we want to write this in the limit definition form, okay, for the Riemann sum. Okay, that would get us the area. Okay, so what limit definition here is equivalent to this? So let's identify some key piece of information. Key piece of information 1, what is our A? It is 3. Okay? Well, if you look here, they all have a 3, right? So that's not very helpful. All right? What is our f of x? X to the 4th, right? Okay, well, if you look here, all of these functions are being raised to the 4th power, so not super helpful either. What is our delta x? Right, 5 take away 3 over n, which is 2 over n. Okay, now if I look here on the outside, could A be the answer? It's got a 1 over n, it needs to be 2 over n, so C as well has a 1 over n on the outside, not correct. Okay, so it's got to be B or D. Which one is it?
It's definitely D.
It's D, okay, because it's got the correct delta x. Again, this is the wrong delta x. It's k over n. It needs to be 2k over n. Okay, and so D is the answer there. Okay, this one is missing a 2. Okay, questions on that one? All right. Whew. Let's keep going here. This is going to be much nicer now. All right. So, for example 4, we're asked to sketch the region corresponding to each definite integral, then evaluate each integral using a geometric formula. Okay, super easy here. Okay, so the graph of 4, what does that look like? A horizontal line that goes through 4. Exactly right. 1, 2, 3, 4. Okay, so there's our function. Okay, f of x equals 4. And we want to do the definite integral from 1 to 3. So 1. Okay, so there's our left hand, our lower limit of integration. There's our upper limit of integration. And so what is the region here that's bounded by the function, the vertical line x equals 1, the vertical line x equals 3, and the x-axis? Well, here's the x-axis, right? There's the function. There's the vertical line 1, there's the vertical line 3. So what's our region? It's what shape? It's a rectangle. Exactly right. With what dimensions?
It's not a square.
Yeah, it's not a square.
Go ahead.
No.
What's the width here? 2. What's the height? 4. So what's this integral's value going to be? 8. So the answer is 8. Okay? That's all there is to that. It's just using the geometric area there. Okay? Let's do this next one. Okay? It's a little bit strange because it's defined in terms of y. All right, so we'll still do this here. Okay. If I plug in 2 for y, 2 squared is 4, 4 minus 4 is 0, square root of 0 is 0. So I get the x-coordinate of 0. So a 2y coordinate is x-coordinate of 0. That's going to be this point right here. Okay. If I plug in a 0, for my y-coordinate, 0 squared is 0, 4 minus 0 is 4, square root of 4 is 2. So I get the point 2, 0. Okay. And then negative 2 squared is 4, 4 minus 4 is 0, square root of 0 is 0. So at negative 2, I also have an x-coordinate of 0, so I have 0, the point 0, negative 2 right there. So this is a semicircle here. This is a semicircle. Okay, it's this kind of semicircle though. I didn't do a very good job drawing it, but you get the idea. Okay. Okay. So now, since we have with respect to y, since it's with respect to y, we're going from -2 to 2. We're going like kind of like a vertical integration here. So here we're doing a horizontal, right, left to right. Here we're going from bottom to top, bottom to top. Okay. And so what's our boundary here? Well, now it's going to be the y-axis that's our boundary, the function, and the vertical line -2 and 2. But there's, I mean, you can see what the region is. It's just this region right here. Okay, it's being bounded there. Okay. So again, this geometric shape is a semicircle. Okay, what's the formula for a semicircle's area? Bless you. 1/2 pi times radius squared. What's our radius in this case? 2. Okay, maybe I could just do this right here. So times 4, which is going to be 2 pi. Okay? Yes?
For this one, if we flip the y values to x values and just graph it the opposite way, that's what we want.
Yeah, it would work out okay. Yes, it would work out okay. It would be okay. Just a change of variable. The graph would look slightly different, but it would be the same region. All right. So again, here we are evaluating those definite integrals by just finding their areas using geometric formulas. Let's try this one right here. All right. Now, x minus 4 inside the absolute value and a minus 2 outside the absolute value. If you remember, that results in a transformation of the absolute value of x. Normally the absolute value of x, where is the point? If you're just graphing absolute value of x, where is the point of that absolute value, or the vertex of it? 0, 0, right? But what is this and this shift going to do? Right 4, down 2. Exactly right. So we'll go 1, 2, 3, 4 to the right, and down 1, 2, and there's where our new vertex will be. Now, how can we get more points? We could plug in points, right? But we can also just use the slope, right? What's the slope of this graph going to be? To the right, it'll be a slope of what? Positive 1. To the left, it'll be a slope of what? Negative 1. So we're going to go up 1, right 1 to there. Up 1, right 1 to there. I'm going to stop because we're only going to 6. We'll go up 1, left 1 here. Up 1, left 1, up 1, left 1, up 1, left 1, like that. So it looks something like this. Excuse me. So now, this is a little bit funky because our graph crosses the x-axis. So we need to come up with, let's first identify our regions that we're talking about here. Remember that the area we're trying to find, this is equal to the area between the curve and the x-axis from x equals 0 to x equals 6. Okay. So from 0 to 2, our curve is above the x-axis, so the region is going to be, there's the x-axis, there's the x equals 0 vertical line, and at 2, so this is going to be our region right here. Okay, like that. But then from 2 to 6, our curve is below the x-axis. All right, so our bottom boundary is going to be the curve. The top boundary will now be the x-axis, and so this is going to be our region right here. Okay, so it kind of flip-flops like that. Okay. Well, what geometric figure is this first shape? Triangle. Okay, what will its area be? Yeah, area equals 1/2 times base, which is 2, times height, which is also 2. And so it's going to be 2 is the area there. And then what about the area for this region? What will it be? Well, it's a triangle, right? So, what is the base of that triangle? 4. Okay, what's the height of the triangle? 2. So 4 times 2 is 8. Half of that is going to be 4. Okay? Now, we're using areas here to find the values of these regions. Okay? So the area, if we're just talking about area, the area of this would be 2, the area of this would be 4. But when we're trying to evaluate this as an integral, we have something that happens here, right? The rectangles that we're adding up in here, right? So if I kind of break these regions up, let me kind of just do a little dotted line here, break this up, all right? The subintervals, they're all going to be a delta x of greater than 0, right? The widths of those subintervals are all going to be positive. We're going from left to right, so just positive subintervals there. The function here is also greater than 0, and so we end up with a positive area. Okay, but here, the subintervals are still greater than 0, right? We're still having positive subintervals here, left to right and stuff like that. But the value of the function is what in this interval? It's negative or less than 0. Which means then if we take our widths, the delta x's, multiply by our heights, right? Take our widths and multiply by our heights, the area is actually going to be considered to be, or the value of this definite integral is going to be less than 0. And so while, yes, the area, okay, the area of this shape is 4, we're going to consider the value of this to be negative because it's below the x-axis. Okay, so below the x-axis, negative, above the x-axis, positive. Okay, so the actual answer here then is going to be 2 plus negative 4. Let me write it this way. The integral from 0 to 6 of the absolute value of x minus 4 minus 2 is going to equal 2 minus 4, or plus negative 4, I'll say, which is equal to negative 2. Okay, so the value of that integral is negative 2. Okay, we take the positive area here, 2, take this area, but make it negative, okay, because it's under the x-axis, and so it becomes negative 2. Okay? Does that make sense? Question on any of that? All right, keep on trucking here then. All right, so with all of that said, now we have definitions for 2 special definite integrals, okay? And like basically these are definitions, right? We don't have to prove them. We're just going to say that these are true because if they weren't true, well, I mean, it makes sense that this is what it would be, right? So for example, if f is defined at x equals a, then the integral from a to a of f of x dx is 0, right? Which should make sense if we have a function. Okay, there's f of x, okay, and we just graph, there's a, okay, and we integrate from a to a. Is there any area between a? No, right, because it's itself. And so we would say then the area here should be 0, right? So it's just going to be 0. Okay? Then simultaneously here, if f is integrable on ab, then the integral from a to b of f of x is equal to negative integral from a to b. Sorry, I think I flipped my things around here. So the integral from b to a is equal to the negative integral from a to b of f of x dx. Okay? So integrating from b to a, our lower limit from b to upper limit a is equal to the opposite from a to b of f of x dx. Okay, so if you flip your limits of integration, then you can just, well, if you start with like from b to a, if you flip them, then you can put a negative out front, and it'll be equal to the original there. Okay, so b to a to b. So in other words, let me see here. If I have like from 1 to 4 of f of x dx, okay, that is equal to negative integral from what to what? 4 to 1 f of x dx. Okay, like that. They're equal with a negative there like that. Okay? All right, some other stuff. Theorem. If a function f is continuous on the closed interval from a to b, then f is integrable on a to b. Okay? So kind of like, again, that when we learned about differentiability, right? Differentiability implies continuity. Well, here, continuity implies integrability. Okay, so differentiability implies continuity. Continuity implies integrability. Okay. So, questions on any of that? We're okay there. All right. Moving on here. We're getting there. All right. So theorem: additive interval property. If f is integrable on the closed intervals determined by a, b, and c, then the integral from a to b of f of x dx is equal to the integral from a to c of f of x dx plus the integral from c to b of f of x dx. So you see what we did here in this case, we took the interval from a to b and we broke it up into 2. we integrated from a to c, and then from c to b. And by combining those two integrals together, it's the same as just going from a to b. Okay? An application of this, we kind of saw it earlier, Clayton?
I was just going to ask you, you said continuity implies integrability,
Mhm.
and differentiability implies continuity.
Mhm.
Is that safe to say that differentiability implies integrability?
Exactly right, okay? By the law of syllogism
I don't know
there,
if we
yep.
could skip that step or not.
Nope, you can absolutely do that. Yep, exactly right. So if we go back to our previous problem right here, okay, for example, what we could do is say the integral from like 0 to 6 of the absolute value of x minus 4 minus 2 dx is equal to the integral from 0 to 2 of x minus 4 minus 2 dx plus the integral from 2 to 6. Oops. Okay, so you can take this one integral that we're trying to evaluate from 0 to 6, and you can break it up into smaller, like sub-integrals, right? From 0 to 6, we just break it up from 0 to 2, 2 to 6. That, adding those two together, gives you that right there, okay? Which is what this says right here, okay? So this is another way of thinking about that earlier problem that we did right here, okay? All right. So let's take a look here at example 6, right? Given that the integral from -1 to 1 of a function is a value of 3, okay, and the integral from 0 to 1 of f of x dx is 5, then what is the integral from -1 to 0 of f of x dx? What must it be? -2? Okay. So how'd you get that, Lander?
I realized that from -1 to 1, it's like the full.
The full interval, okay? So you can say, for example, that the integral from -1 to 1 of f of x dx is made up of the sum of what? The other two, right? We can say, okay, well then from -1 to 0 of f of x dx plus the integral from 0 to 1 of f of x dx, right? Are we in agreement here that this is so? -1 to 0 plus 0 to 1 will give us -1 to 1 of those functions. Okay, and now we can just substitute in values. Instead of saying -1 to 1 f of x dx, what's that equal to? It's 3, right? And from 0 to 1, which is this, that's just 5. And so then what does this equal? Well, solve, right? Just subtract 5 from both sides. And you get -2. Exactly right. Okay. Questions on any of that? Okay. Just what we want on a Monday morning back from break is really intense calc notes, but there they are. So, this last page I leave to you, for you guys to try right now, okay? You have a good 13, 14 minutes, okay, to get it done here. So give it a try, okay? You're going to estimate from 0 to 8 using a left endpoint. You're going to estimate from 0 to 8 using a right endpoint, a trapezoidal with 4 subintervals for each, okay? And then finally find the exact value, okay? Again, using geometry to help you, right? Using geometry. Maybe draw a picture. We can use your graph, I guess, your curve, your graphing calculator to help, I guess, if you want. Okay, feel free to use your graphing calculators here to help if you'd like. Okay, feel free to use your graphing calculators here to help you if you like.
Do we have to get actual answers?
No, if you want to just set them up, that's fine. Okay. But go ahead and give this a try. Whoops. Bless you.
Chad,
Do you still live in the same place?
yes you do.
I'm looking at your house now. I was
Yeah.
great song.
Typical man, right?
Typical man.
Typical man.
That was last time. Or going down to your basement.
If you want some help, just get me
Oh, we did though.
I think we got like, is that a 9?
Where you used to make that long trip all the way to my house, the townhouse, and then my parents would be like, hey, you
That's
got
be
Are you okay? Come
not
on.
5. Because you left. It was 8. Okay, so then those will cancel. That's a 0. And then plus the cancel.
I feel like such
You did it on purpose.
a I know, but I still won't.
Why? He told me to walk to his house, and then I got there and I was like, yeah.
How wide
There's
is
6 pins all the way up there. I don't know.
What's 12
So, for the first interval,
left.
Chill with
Take
that.
half of that.
0, right? And then out
I don't know
on
what it was. Did you get 40 for
2,
two?
so 2, right? 0 to 2. If you want to use the left end point, it's f of 0.
Because the other side
So
would be
f
negative.
of this, f of 0. That's your moment. So left of 0 would be negative 4. So you choose one right.
So fucking.
And then 0 there, right? And to the next one, so that's like
Yes.
0, 2, 4, and then that's f of 6, right? You're gonna have 2 more, so 6. So
At least I don't say 7 for 5 minus 2.
Alright, honestly, I just like looked at the numbers, I saw 5 and 2, and I was like 7.
wait.
I didn't even think about what he had to ask. I just what I thought it was.
This is right. This is right.
7.
That's a negative 4.
Is it reasonable? Yes.
What was like it's second grade basketball.
Rough time.
So this one I want to actually find the exact value. So what that means is we
Yeah.
what
Had me thinking for a second.
Oh my god.
graph.
It's okay. I do a lot of stupid mistakes.
Yeah, you do.
I didn't have a problem with that on my homework.
Yes. Yes.
Good woman. Good woman.
At least they're saving.
Question
the
for
treatment.
Celia.
Just quick thing. I did my problem set on that.
Oh, okay, the one that's due today, you're saying? Alright, so if you want to just get it to me tomorrow, that's fine.
Okay.
Yeah.
Probably should just graph it on.
At least they're saving the trees. Green the wall.
Oh wait, no, I never did.
Look at your. Or you know.
So don't integrate.
No, you're right. I'm on
The area of the region is the region created by this function, 2x minus 4. So like you're gonna draw it.
So is the
straight
borax
line.
in it?
So let me see how you evaluate this. I think maybe you had some errors with that, so let's see. So f of 2.
He's having some trouble with that.
So let's try over here.
Because I'm trying to find out what in the hell
So if you did
that
that,
is.
It's 1/2 times 4 times 2. It's that triangle, that's right
That
there.
is not a 2.
That's definitely
you
a
had 2 times this quantity.
Carter,
2. It's a 2. The answer's right. Isn't it a 2?
look at the number.
So then
Tell me that that little scribbly thing, that little.
It doesn't look.
There's nothing like a 2 whatsoever.
Then it doesn't fucking matter.
Actually, it does. 'Cause you can't read it.
Oh, wait, it times the 4.
It kind of looks like it.
Thank you.
It looks more like a backward 6 though.
I did.
Oh yeah, because Mr. Thompson couldn't read it. He got the answers right.
I'm not
Mr.
all the
Thompson
answers right. Nope, dude, I couldn't read it. Nope. Yep.
That was honestly one of the funniest
It's hilarious.
things. And then other than the fact that like every single day.
I think he still gave me the points for it. Though.
Okay.
Luke's really
Just in the interest of time here, I want to give us a chance to be able to ask questions. All right, so there are your sums for 7a and b, 16 and 48. Okay, 16 and 48 there. Okay.
I did the same.
I wrote down the first equation.
Letter C, 32. Okay. And then letter D, using geometry, also 32. Okay. Will the trapezoidal approximation always match the exact value? No, but because our function here is nice and linear, okay, our little trapezoids are going to perfectly match that linearness and get the exact value, okay? So it's going to give us 32 in that case. If this was curved, this trapezoidal roll still wouldn't work. Okay?
Tell me to go take a nap next period.
So, yes. Thank you guys for bearing with me. Yes, Emma. Set requests. Yeah. Also, you found your pencil pouch?
Yes.
You didn't need to find it.
Can we get a break tomorrow?
Yeah, after we take
After the
the
quiz?
Yes. Should be pretty laid back, I think.
How long is the quiz? Like,
Ooh, time-wise, right. Let me see if I actually got 25 minutes for the quiz tomorrow.